All right, so in this lesson, we're going to be taking a look at a lot of our basic terms and concepts that we're going to be using in geometry. Specifically, we're going to be looking at all items that are based around the ideas of points, lines, and planes. Now, in any field of study, you're going to have some basic concepts. In mathematics, we call these the undefined terms, simply because in order to really talk about them, you would have to use items that others would describe this. And really, in geometry, everything that we are going to do is based around the ideas of points, lines, and planes. So what exactly does each of these mean? Well, a point, for starters, is a single location in space that has no dimensions. Now, typically when we are referring to a point, we will place a small dot with a letter next to it. So I will call this point A. But even that dot, because we can see it, is too large to truly be a point. It's the best representation that we can come up with. But any fixed location, whether it be on a number line, on a grid like the XY graphing grid, or in three-dimensional space, any singular location can be defined as a point. Okay? Next up, we have a line, which is a straight path that extends in two opposite directions infinitely. Line has length, but no width or depth. So when we take a look at a line, there are many different ways we can do it. We can set a pair of points, let's say M and N, and the line is the straight path that connects them. Now, this is being done freehand, so that path I drew does have a little bit of a waver in it. But when we talk about this, we can talk about the line in terms of points that it passes through, and you will notice that at both ends, I have placed an arrow indicating that does go on forever. When I talk about this line, I can talk about line MN with a small line indicator above it. Another option is I could call this, at the end of the line, I could put a lowercase letter, and then I could just talk about line T, in which case I would actually write out the word line and then put a T after it. So we have a lot of different options when it comes to naming lines, but for a point, we do have just the one. Our last undefined term is plane, which is a flat surface that extends without end but has no thickness. So now we're looking at length and width, but no depth. A lot of times we can think of a plane in terms of the top of a table, a wall, any flat surface is a portion of a plane. Now, when we're representing these in geometry, what we do typically is we draw a simple basic shape, and we can name it by either a singular letter in the corner without a point associated with it. So this would be plane P, or let's say we have R, S, and T. We can call it plane RST, naming 3 points that are on the plane. Now, when I say plane RST, I am choosing to do it alphabetically from the letters or the points given. I could also call it plane RTS, STR, SRT, any combination of those points that are on my plane. So even more options than what we had. So point, singular location, line has length, plane has length and width, but nothing here as yet has depth. So it's interesting when we're working in geometry using visual representations that how things appear can make a big difference. So we could talk about points being collinear or coplanar. Now, collinear would mean that they lie on the same line. So in this, points A, B, and C would be collinear. They appear to be on that same line. For coplanar, we're looking at items that lie on the same plane. So A, B, and D are potentially coplanar here, or A, C, and D. Also, we have what appears as D, A, and E. But when we start looking at these representations, how things are isn't always what's there. So let's take a look at a different perspective of plane P. So here we can see that if I rotate this plane just a little bit, that I still have my points A, B, C, and D appearing on the plane, but E is actually suspended in space over top of the plane. So from one perspective, it does look as though all 5 of these points are coplanar, but from this other perspective, it's only the ones that are there. Now, earlier I described that a line would connect 2 points. So even though line AB or line AC or line BC is the only line that is shown in this representation, it is not the only line that exists. I could just as easily draw a line between A and D and put my arrows on the end, and that would be another line. So one thing we're going to have to learn to do is look for what could potentially be there and still hold it with the same merits as what is actually shown. Okay? So what can we do with these items, our points, lines, and planes, as we start to move forward? Well, one is, as I was mentioning, how many different ways can we really talk about an item? So other names for certain items. Now, points are always just points, but when we start to talk about lines and planes, we have options. So in this representation, we do have this line here drawn in. We do have this line here drawn in. Notice in this space that the line appears broken. The dotted section there is to indicate that that portion of the line falls behind this plane that has been drawn in. Okay, so what if I am talking about line RQ? What are some other ways that I could talk about line RQ? So pause the video here and see how many different ways you can come up with. So as I look at this, when I look at line RQ, I could also be talking about line RS. I could be talking about line QS. I could talk about line QR, line SR, line SQ, and of course I could say line L, because at the end of this is that lowercase letter indicating the name of the line. Okay, and we could do a similar exercise with line M. How many different ways could we talk about that? But what if I were to want to shift my focus? How many different ways can I talk about plane RQV? Well, with RQV, I'm looking at this set here, which all appear to be on this plane that is drawn in. So what I can do is I can say what other points are on there. Well, I would have plane RSV, plane QSV, plane VQR, which is the same letter set that we had at the beginning, just in a different order. And we could take any combination of these letters. I could also look at plane P, because buried here in the corner is a single letter without a point associated with it. Now, are there other planes here? Yes, there are. We could make a plane that uses line NT and then passes through Q. So it'd be a vertical set plane that goes in this direction where this meets. Think of a pair of books or a pair of pages on a book coming together at the binding. Okay, so we have what's shown, and then we do have other options. Okay. So when we're talking about these overall concepts, we have a lot going on there. But lines a lot of times can be broken down into smaller pieces. So what do we do with those smaller pieces? Well, when we're looking at what I call sublines, we have these concepts. We have the line segment, the ray, opposite rays, and then we can talk about the length of a line segment. So a line segment is a part of a line that has both a starting and an ending point. Now at the bottom here, we do have a line, we'll call it line DF. Well, if I'm looking at segments of this line, I could talk about segment DE. And I put a stick over top of it with no arrows on either end, indicating that it starts at D and ends at E. Okay. I could also have in here segment EF or segment DF. Okay, and I could reverse these letters. I could say segment ED, segment FE, segment FD. But those are all the smaller pieces of just a section of this line that could be taken out. Okay. Next, we have array. And this is simply a part of a line that has a starting point, but no ending point. A lot of times when we talk about rays, our minds go to thinking about sun rays. These are rays of light or segments of light that start at the sun and then head out from it in one direction and theoretically would never end. They just get more dim as they go. So in our representation below, when we talk about a ray, we talk about its starting point and then direction of travel. So I could say ray, so notice there's an arrow on one end but not the other. I could talk about ray DE. Now this ray starts at D, heads towards E, and then keeps going. That would be the same as saying ray DF, because it starts at the same place, goes the same direction. Now if I were to start at point E, and then head towards F, that would be a ray that starts here and goes that direction. But I could also talk about ray DE. Let's scratch that. I could talk about ray ED, which is different than ray DE because this ray DE starts at D and heads towards E and keeps going. Ray ED starts at E and heads towards D and keeps going. So the ordering of the letters on rays is very important. And with those two, we do have this concept of opposite rays. And these are two rays that share the same starting point, but then travel in opposite directions. It's not just that they travel in different directions, but they need to be completely opposite. In our representation below, the only pair of opposite rays we have are rays EF, which starts at E and moves to the right, and ray ED, which starts at E and moves to the left. Okay. There are other rays in there, we just don't have the letters to be able to talk about them. Now, something we're going to talk about in a later lesson, length of a line segment, goes back to the concept of line segment itself, but we're actually putting numbers to it in measurement. And the reason I talk about it here is for the notation. If you ever see just the pair of letters without any representation over them, so D and E side by side like that, if I have an arrow over top, arrows on both ends of a stick over top, then I'm talking about line DE. No arrows, we're talking about line segment. Arrow on one end, we're talking about array. But if I have nothing, now I'm talking about the length. So just be aware of that different notation. Okay. So what can we do from here? With all these different pieces, our points, our lines, and our planes, we can start talking about how they interact. And we're now being introduced into our concept of postulates, or in some vocabulary, they're called axioms. So just a quick note, a postulate or an axiom is a basic building block idea. I like to refer to them as no-duh statements. These are items that if you look at them for just a very short amount of time, you can see that what's there really should be obvious. Now, later in geometry, we'll start taking some of these postulates and mixing them together, and we come up with what's called a theorem, which is a slightly more advanced idea, but it goes back to those postulates themselves. So in this lesson, we are having 4 postulates. We're going to talk about all of them now, and they do talk about the interactions of points, lines, and planes. So our first one, which I'm going to call postulate 1-1, which simply states that through any 2 points, there is exactly one line. Since a line is a straight, direct path of travel, if I pick 2 points on a plane or 2 points in space, there's only one way to go directly between them. Okay. Next, postulate 1.2, which states that if 2 distinct lines intersect, then they intersect in exactly 1 point. And the reason this says if is because we do have lines that never intersect. 2 types. There are parallel lines, which are lines in a plane that never intersect, or there are what are called skew lines, which are lines in different planes that never intersect. And we'll talk about that in a later lesson as well. Okay. Next, postulate 1.3, which moves us up to talking about planes. So if 2 distinct planes intersect, then they intersect in exactly 1 line. Because planes are infinite, they would run into each other and create a marcation that is infinite as well. Think of the corner of a room where your floor and wall come together. That'd be the intersection of 2 planes. But not every pair of planes intersect. Think of the ceiling and the floor in your bedroom. You now have a set of parallel planes. We can have parallel planes just like we can have parallel lines. Okay. And our last postulate for this round, postulate 1.4, which states through any 3 non-collinear points, there's exactly 1 plane. So 2 points establish a line, and then if I pick any other point off of that line, I get a plane. If I have 3 points that are all collinear, think of taping a piece of paper to a string. Any direction I twist that string, I would have a different plane. So if my points are collinear, they're all on the same plane. If they're not collinear, then I define a specific plane. Okay? So how can we put these to use? So in this representation, I have line AE, I have line BD. Now these two appear to intersect, and their intersection point is at C. Now there is no dot shown at C, but it's the location of the letter and the intersection of the 2 lines. It becomes an assumption in our representations and drawings that C represents that point of intersection. As AE travels this direction or this direction infinitely, and then BD travels here and here infinitely, these 2 lines will never touch again in all of space. So C is their 1 point of intersection. Okay. Similarly, down here, we have 3 points that are not collinear. S, T, and R define this blue plane. S, T, and W represent this yellow or yellow-orange plane. And where those 2 planes intersect is line ST. Now this plane will travel out forever. This plane will also expand out forever. But the only place these 2 planes will intersect is at this line ST. So what happens when we move things up into 3 dimensions, which we were starting to have? So in this hexahedron, and we'll talk about that much later in geometry, we have the 6 walls that make up the box, basically, and we can start talking about our items. I have line segment AE, but there is a line that passes through here. Line EH, well, those 2 lines only intersect at point E. Similarly, I could say for giving a point, what 2 lines intersect at point B. Okay? If I want to talk about point B and what two lines do I see intersecting there, I can talk about line AB. I can talk about line BC. They do share that point B. But I could also say AB and BF as intersecting there. And now I'm looking at across the top and down the side. But they do come together at point B. There's a lot of different items that are in here. We have the lines, the line segments that we see, but we could also talk about line DF, which would cut from across opposite corners inside of this box. So what happens if we are given a representation and asked to draw in plane JMP? Okay. Well, first thing we need to do is find all of these points. J is here, M is here, and P is here. So we're looking at an item that will cross-cut this box, and what I can do is draw, Q will also come into play here, across, and then lightly shade in the piece so I can now see that plane cutting through the box. Okay. Again, we do have the pieces in our representations that we see and that are there, but do be open to the idea that there are others out there. As long as they meet the definitions set forth in those postulates, we do have planes and we do have lines. So this lesson was a little bit longer than ones I tend to do, but we had a lot of materials. Do learn these materials and ways that we write things, because this is going to be the foundation for all the other items that we take care of here in geometry.